the quantum particle. And when an operator acts on an eigenstate or eigenfunction, it will give you an eigenvalue. Eigenvalue is like, the set of allowed measurable quantities, okay, discrete values. And in today's lecture, which title is Application of Quantum Physics or Quantum Mechanics, and here we will study extensively 5 well-known problems in quantum mechanics which we can solve, right, without any approximation. That means we'll start from Schrodinger equation, and then we'll show that the quantum system will have discrete allowed energy levels, okay, which is one of the landmark or features of quantum system, discrete energy level. So as I said, that we should work on 5 important problems, and to make the thing much simpler, we should deal with one-dimensional problem, and whatever result we'll get at one dimension, we can easily extend into the 3 dimension. Okay, and as I said, if you remember in the last class, that most of the systems, right, or the practical system or practical quantum system, the potential energy does not change over time. So therefore, we should deal with time-independent Schrodinger equation. Am I audible?
Yes, sir.
Yes, sir.
So in one dimension, so this is the time-independent Schrodinger equation, psi x. Do remember this psi x is the total wave function that describe the quantum system or quantum particle, and E is the energy associated with the particle, V is the potential. So now we'll solve it and we'll get that the quantum system must have discrete allowed energy levels. Discrete energy levels, and when they will be allowed, right, physical or in the sense acceptable, they will be called eigenenergy. And what would be the wave function? A e to the power I kx that we have already seen the last class, or in real form either a1 sin kx or a2 cos kx, or the linear combination of a1 sin kx plus a2 cos kx. Okay. So we should begin with this Schrodinger time independent equation. But the question here is how we'll solve it. So here are some important steps one should keep in mind while solving quantum mechanical problems. Any quantum system, any problems related to quantum particle or quantum systems. So what are these steps? So that I have listed down here. First, if you look this Schrodinger equation, right, and if you remember the characteristics of the wave function, so one point is the wave function must be continuous in all position, all portion in the space, including interface of two media, right? So therefore, it is important that since the potential energy is a function of position, how the potential energy varies over position. Once we figure it out, then it would be easier to solve this first order ordinary differential equation. Okay. So, so in your exam, if a question will come that time independent Schrodinger equation, is it ordinary differential equation or partial differential equation? Then immediately you will tell that it is an ordinary differential equation. However, general Schrodinger equation should be partial differential equation. And how many variables are associated with general Schrodinger equation? It depends on whether you are working in one dimension or 3 dimension. If you are in one dimension, then there are 2 variables independent. One is time, another is position, let's say x. If it's a 3-dimensional Schrodinger equation, then you must have 4 independent variables. 3 for position like x, y, z, and 1 for time. Is it clear? Yes or no?
Yes, sir.
Sir.
Yes, sir.
So the first important thing is, since the potential is a function of position, we need to figure out the potential in different regions. And once we figure out the potential, then it will be easier to write down the Schrodinger equation in these different regions. And then we have to solve it. And so now when I talked about different regions, once you figure out the potential and the interface, the wave function must be continuous. Therefore, we should solve this Schrodinger equation in different regions with appropriate boundary condition. That means it must be continuous, first derivative must be continuous. Okay. And once we put the boundary conditions, and then the allowed wave function will automatically come out when you solve this Schrodinger equation. And since this allowed wave function is known as a eigenfunction, so that means when you solve Schrodinger equation putting boundary condition, you will get the eigenfunctions. And you have to, since the wave function is square integrable, we need to use this square integrable condition over wave function, and then we will get the normalized eigenstates. That means the probability of the finding particle all over space is 1. So this is called square integrable, or sometimes people call normalized condition. Okay, and then once you impose normalized condition, what you have to find, then you will get the allowed energy levels, which is called eigenenergies. So these are 6 important steps one should keep in mind while solving any quantum mechanical problem. Okay, and if you study a lot of quantum physics book, so you must conclude that you should deal with at least these 6 important points. Okay, focusing on the boundary conditions, what does mean appropriate boundary condition? That I have written down here. So now we have present, potential energy or psi x, because both of them are a function of x. If you look this Schrodinger time independent equation, potential energy and this wave function. So you should figure out how the potential energy varies over these two media, and x equal to x naught is the boundary. So it means if the psi1 represent wave function, the first medium, and psi2 is the second medium, it must be continuous. At x equals to x naught, it should satisfy the first derivative is also continuous. Okay. So so these are 6 important steps. Then the next is, as I told you, there are 5 important quantum mechanical problems which are exactly solvable. That means without making any approximation, we can get the wave function. That means the allowed eigenwave function, so allowed wave function known as eigenfunctions or eigenstates. And if we make the linear combination, we'll get the total wave function. And we'll also get discrete allowed energy level, which is known as eigenenergy levels. So let's look at what are these problems. The first one is particle in a box, right? So you can say the pet name or nickname, and it is in fact a particle which is trapped inside an infinite potential well. Okay, and then quantum harmonic oscillator, then the quantum free particle, and then a particle, quantum particle, which C potential state, and a quantum particle which C potential barrier. So these are 5 exact solvable problems in quantum physics, and we'll solve one by one. In fact, I will solve explicitly the first one, the particle trapped in an infinite potential well, and this is very important. For example, the atoms, the simplest atom, the hydrogen atom. So if you remember, the potential is like here, right? So you have a nucleus, the potential energy which vary 1 over r minus 1 over r, right? And you can say this is potential energy, and this is your position r, right? So this is energy or potential equal to 0. So it's like that electron is trapped inside an infinite potential produced by a nucleus. Okay, so this infinite potential well has directly application to atoms, and it will explain how electrons are in bound state in atom. So therefore, we'll solve explicitly this one, and one can use the same procedure to solve other 5 problems. Is it clear to everybody?
Yes, sir.
Yes, sir.
Yes,
So
sir.
you should focus on, right? So this one. Okay, so let's work on this, and we'll also figure out the potentials in different region for all cases, right? As I said, I will solve or will see, right, how the allowed wave functions, it means eigenstates or eigenfunctions, and allowed energies, which is known as eigenenergies, will appear when you solve this Schrodinger equation. That we'll see explicitly by solving this one. Okay. So this red represents the particle, and what does mean infinite potential? Well, that means if you look at the top, like for example, if someone is here, right? So let's say this. So this double-headed or this single-headed arrows implies it goes to infinite, right? So it means the person who is standing here, he or she will see that infinite wall. Okay, and in reverse way, if someone is standing at top, here we will see that this has infinite depth, so therefore it's called infinite potential wave. And the mathematical representation is like this. So within 0 to a, the potential energy is 0, and when x less equal to a, that means this region the potential energy, this is infinity, and x greater equal to it is infinity. Okay, and here it's 0. Okay, so it means as I said, whether you are looking at top or looking from the bottom, you'll see infinite height or infinite depth. So therefore, one can say the particle is trapped inside an infinite potential wave. Is it justified? Is it clear to everyone? Why is called particle is trapped inside an infinite potential wave?
Yes, sir.
And then the quantum particle in a harmonic potential. What is harmonic potential? Half m omega square x square that we have already seen in oscillation chapter. And this, what is the value of x? Minus infinity to infinity. It's a parabolic equation, and you can draw parabolic equation like this. Again, this double-headed arrows, both sides shows that it goes to infinite, right? So and this represents the particle, right? And particle cannot escape since the potential wall is infinite. The particle will be this harmonic potential, and this has application on the atoms or molecules. They vibrate inside a metal. So as you know from the thermodynamics, if we increase temperature of a metal, what will happen? The atoms that present, they will start oscillating around their mean position, right? Following this harmonic potential, they won't leave their mean position. So for example, if someone wants to explain the specific heat associated to the metal, okay, or any thermodynamical properties, one should deal with this harmonic potential. So it has direct application to metal. And then potential steps. For example, if the particle is here, right? So by the way, if you look all the schematic diagram, this strip region says that potential is not zeros. Okay, that means potential is some potential is here. So similarly here, so this are it's like a step, right? So it is like a step. So here the potential height is V naught in this region. The mathematical representation is like this. When x is less equal to 0, potential is 0. When x is greater than 0, the potential is V naught. Okay. And the potential barrier we have here. And you can see this is a barrier, a square barrier. Okay. V naught 0 less than x less than a 0, x less equal to x equal to. And then the last one is the free particle. That means there is no potential where the potential is 0 everywhere. And as I said, the red, bold, this, sphere or spherical circular, this field circle, that represents the position of the particle at an instant of time. Okay, it could be here, or it could be here, it could be here, or it could be here, or it could be here, or somewhere, depending on the energy associated with the particle. So now, what we see finally that we have figure out the potential at different regions for all these listed problems. Okay, and as I said, we'll solve only one of them, like infinite potential well, and the rest you will follow the same procedure to get the eigenstates as well as energy eigenvalues. Is it clear to everyone?
Yes, sir.
Yes, sir.
So now the question remains, why it got the name particle in a box? What does it mean? So in order to understand here, as I said, since it has the infinite potential depth, if someone is looking from the top, and since it is infinite depth, so if you leave something inside, then it will never ever escape from this potential well, right? And the things will ever remain in this infinite potential well. It's like if you keep something inside a box, right? Box, and if you close it, the items, for example, your precious item, let's say necklace or diamond, once you keep in the box and close it, and that precious item will never get missed out from this box. It will be remain. So in that context, sometimes people call that particle is inside a box, because the particle will never escape from this potential well. Okay. And as I said, the applicable to bound system, for simplest case, hydrogen atom or any atom. Okay. So now we have to, the first step is to figure out the potential that we have already done. And we have three regions, region 1, region 2, region 3. In region 1, potential is infinite, region 2, potential is 0, region 3, potential is infinite again. Okay. So now, if you look this schematic diagram, one thing you will conclude that at x equal to a over 2, if someone is standing here at x equal to a by 2 and looking the left side, and if here she turns 180 degree on the right side, what will see? You'll see the exactly same scenario. So that means this system is symmetric at x equal to a over 2. It means, or in other way, if you fold it at a over 2, it will exactly overlap the other half of the other half portion of this diagram. So in that sense, the region 1 and region 3 is symmetric around a over 2. So instead of solving these two regions, right, it would be convenient to solve Schrodinger equation in the first region. Whatever the solution we will get in region 1, it will also to region 3, because it's symmetric around a over 2. If you fold it around a over 2, it will exactly match the left portion of the schematic diagram. So this is called the mirror symmetry. For example, a sphere, right, its mirror is in a symmetric around its center, right, and a cube is mirror symmetry. You can, if you move from one corner to another corner diagonally, so it is a symmetric around that diagonal, or any axis which passes through the center, right? For example, from top to bottom, top face to bottom face, that that goes through the center of the top face, and which comes out the bottom of the center of the bottom faces. And if you rotate, then you'll see that nothing will change. So in that sense, that that those system has mirror symmetry. Okay. So in short, we need to solve Schrodinger equation in region 1 and region 2, and we'll get the eigenstates. Okay, no need to solve region 3 because region 1 and region 3 is mirror symmetry around A over 2. Am I audible?
Yes,
Yes,
sir.
sir.
Audible.
Yes, sir.
So now we have this Schrodinger equation, and if you remember that I have been telling you from the very beginning, whenever you have any notation symbol, you have to explicitly mention them. M is the mass of the particle, E is the energy of the particle, psi is the wave function associated with the particle, h bar is the reduced Planck constant, and x is the position of the particle at any instant of time t. So psi1 wave function, the first region which is outside of the box, region 2 inside of the box or inside the potential layer, or you can say inside the box, and psi 3 is outside of the function. And I said the region 1 region 2 are symmetric about axis E over 2, and therefore instead of solving the wave Schrodinger equation in region 1 and 3, it would be appropriate to solve any one of the region. And as we have already named that region 1 and region 3 is the outside the box, then we'll say that we need to solve the Schrodinger equation outside the box. Let psi 1x, psi 3x, let represent psi naught x. And in the box, that means region 2, psi x. Okay, we just redefined it. Okay, the psi x, now it's psi naught x. So let's first solve outside the box. Vx is infinite, x less equal to a, x greater equal to a. It means the potential is much greater than E, and since greater than, then what would be the Schrodinger equation? If we make this is a positive quantity, what will have? The negative sign will be here. Okay, so now this is a positive quantity, and inside box potential is 0, and therefore Schrodinger equation here. So now we have Schrodinger equation in the both regions. The step 3 we have done. We have written down the Schrodinger equation. So now the step 4. Sorry, step 2 we have done. So now so this is step 2. Write down the Schrodinger time independent equation in different regions that we have done. And then the step 3 to 6. We have to solve the Schrodinger equation. Equation 1 can be rewritten. I can define Vx minus alpha equal to alpha square. I can rewrite like this, where alpha square equal to 2mv e over h square. Okay, so now it is a positive quantity. Okay, so now it is second order ordinary differential equation. We have already solved out ordinary differential equation in oscillation chapter. So what we have to do? We have to start with initial guess solution, and then the solution will be a1 e to the power alpha x, a2 e to the power minus alpha x. Okay, where alpha is this. Okay. And then since in the outside the box potential is actually infinite, when Vx goes to infinite, so in fact this is a function when Vx is goes to infinite, then alpha will goes to infinite. So what does it means? The a1 e to the power alpha x goes to infinite. Okay, so now the one of the wave function goes to infinite. But if you remember the characteristic of the wave function, that wave function should be finite, it should not be infinite. So this one is not physically acceptable solution because it goes to infinite. So not an acceptable wave function because wave function must be finite. Is it clear to everybody? Why we are not considering this portion of the solution? Because it blows to infinite.
Yes, sir.
Okay, so this we cannot consider this solution. Okay, and then what would be the wave function? A to e to the power minus alpha x, the second part of the solution. And again, when alpha goes to infinite, psi naught x goes to infinite. What does it mean? So psi naught x goes to infinite. What does it mean? It means that particle cannot be found outside the box. That means particle cannot be found in region 1 and region 3. Okay, so it means the particle should be forever inside the box or inside the potential well. So that's why it's called the particle is inside box. It will never escape from this infinite potential oil. So now mathematically we showed that particle must be inside the potential oil. Well, so therefore the particle will never escape from this box. So now we sure that the probability of finding the particles outside the classical forbidden. So here I use a term called classical forbidden regions. What does it mean? So when there is a potential barrier in classical physics, we will find nothing because the barrier is high compared than the energy of the particle. So therefore it's called classically not allowed. But in quantum physics, we'll see that there is a certain chances that particle can be found inside classical forbidden regions. So that's why the electron can get tunnel. Those who know about superconductivity, so that case actually the electron will get tunnel through the barrier potential light. And the detailed solution we'll get when we solve this one, the potential barrier, right? So this one, for example, so this is the energy of the particle, and energy of the particle is less than V naught. Then we must expect that particle will be this side of the potential well. But is in reality, depending on the width and height of the particle, there is a certain probability that particle could be found on the other portion of the potential, because the particle can get tunnel although the energy is less than the potential height. It is possible in quantum for the quantum particle, but classical particle, it is not never possible. So therefore, it's called classical forbidden region in classical physics. Okay, so now we, mathematically derive that particle will never ever found outside the box or in region 1 and 3rd, which is classical forbidden region. So the particle should be inside the box. And we need to solve the Schrodinger equation. Yeah. So let's redefine this is k square, which is 2m over h bar square, right? And then the solution will be c1 e to the power ikx, c2 e to the power minus ikx. And what is the general solution? The linear combination of these two. And then we can re-retain this in terms of sine and cosine function. Okay, so here you find what is the value of a, what is the value of b in terms of c1 and c2. Okay, you can take it homework and find. So in short, the general solution is a sine kx plus b cap cos kx by solving this ordinary differential equation. So now, what is the next step? We need to put boundary condition over this Schrodinger equation. Okay. So what is the boundary condition? At the left boundary, if you look that this is the left boundary, so it means since we defined it psi naught x at x equal to 0 must be equal to psi x at x equal to 0. And right boundary, psi naught x at x equal to a must equal to psi x at x equal to a. So this is the left and right boundary. Okay. So now, this is the when we deal with the left boundary, yes, sine kx b cos kx x equal to 0. And what is the y function in the outside the box? This is 0. We have derived psi 1x is 0. And when we put, what will find the b equal to 0, the coefficient b equal to 0. So now, what would be the equation 5? This general solution, since the coefficient b equal to 0, then psi x equal to a sine kx. So only mathematics, nothing great. And when we put the right boundary condition, psi x equal to a, the third region x equal to a, because the wave function are the outside the box, that means the third region is 0. So 0 right hand side, left side a sin k x equal to a. So it means a sin k equal to 0. Is it clear to everybody? Did you understand how we get this relation?
Yes, sir.
So what does it mean? It means that we have two factors or two entities here, a and sin k. So this implies that this will be 0, either a is 0 or sin k is 0, or both of them will be 0. Okay. So but I'll tell that a cannot be 0. Why? Why a cannot be 0? If you put a is 0, irrespective of whatever value of x or wherever you are inside the box, the solution is 0. That means psi x equal to 0. So if psi x equal to 0, what does it mean? The particle is not inside also box. Then why we are solving? It means particle is not inside the box. So in mathematical language, when we put a equal to 0, it's called trivial solution. So we should deal with non-trivial solution. As I said, when we put a equal to 0, that indicates the wave function is 0. That particle is also not inside the box. Okay. So particle is not inside the box. Then why we are solving? Particle, we know the particle is not outside the box because the infinite potential way, and we derive mathematically. Now, if you put a equal to 0, that means the coefficient, and then it says that particle is not also inside the box. So, what we are interested to know that particle, what would be the wave function if the particle is inside the box. So, a cannot be 0. So, it means this product will be 0 when sin k equal to 0. When sin k equal to 0, it means k equal to n pi, n equal to 0, plus minus 1, and plus minus 2, and so on. That implies k equal to n pi over a. Okay, provided what are the n value here. So now you can see that the discrete values already appeared here. Okay, and that will finally lead to you the set of allowed values. So now once you substitute value of k, what would be the wave function? By using equation 5 and 6. What is the equation 5? This one 6. This is 5. So a sin k, putting the value of k equal to n pi over a, we'll have this. So psi x equal to a sin n pi x over a, wave function inside the box. Okay. So now, as I said, once we solve the Schrodinger equation, we'll get the total wave function with n equal to 0, plus minus 1, plus minus 2, plus 3, and so on. Excuse me. Okay. So then the next question is, we need to find out the allowed wave function. That means the eigenfunctions. Then we might ask question ourselves, are all these values allowed? N equal to 0, plus minus 1, plus minus 2, plus minus 3, and so on? No, all these values are not allowed. For example, when you put n equal to 0, this means when you put n equal to 0, irrespective of any position, this psi x equal to 0. Again, it's a trivial solution. So psi x 0 means the particle is not inside the box. So hence, we should not consider n equal to 0. So n is equal to 0 is not allowed. Got it? And so therefore, then other values are allowed. Plus minus 1, plus minus 2, plus minus 3. And since we threw out the non-allowed values and the rest are allowed, hence we have allowed wave function or eigenstate or eigenfunction as per the definition. Is it clear? Am I audible?
Yes, sir.
So now you throw out non-allowed values, and the allowed values will give you the allowed wave function, hence eigenfunctions. So the eigenfunction psi x equal to a sin n pi x over a, provided n equal to plus minus 1, plus minus 2, plus minus 3, and so on. And since the index n is appearing here, so it is appropriate to use an index n over here. And this index n represents the state or wave function, those wave function that are allowed. The psi nx for any one of these values of n will be an allowed wave function. Hence, when we put n equal to either plus minus 1, plus minus 2, plus minus 3, and so on, that will lead to your allowed wave function or eigenstates or eigenfunctions. So now we see that when we solve the Schrodinger equation, we get allowed wave function. That means the eigenstate. That was our main objective, to get the eigenfunctions. Okay, and then we can construct wave function by using these eigenfunctions. Just simply the linear combination, as I said, with some I equal to 1 to n. We have the coefficient psi I and psi I x. Okay, and this psi I that represents the eigenfunction eigenstates. So now we can now construct the wave function from the eigenfunctions. Okay, and one more important properties about eigenfunctions, that they must be linearly independent. Okay, so eigenfunctions must be linearly independent. So what does it mean, linearly independent? So it means that a function, right? Let's say in mathematical language, so we have let f of a function f of x, right? And if we can convert f of x, let's say some a1, let's say gx plus a1 gx. So if we can write f of x equal to a1 gx, so this means the f of x and gx, they are dependent. And since a1 is the linear factor, it's called linearly dependent. That means you can convert f of x function in terms of gx and vice versa. Okay, this is called linearly independent. And if you can have f of x, let's say a1 gx square, then it's called not linearly independent. They will be non-linearly dependent. Okay, they are no longer be independent. So let's check whether all these eigenstates or eigenfunctions, they are linearly independent or dependent. In fact, the positive side of the eigenstates, it means when we use n equal to plus 1, plus 2, plus 3, they are actually linearly dependent the negative side of the wave function. That means n equal to minus 1, minus 2, minus 3. So now here is the proof. When you put n equal to 1 plus 1, we have a sin pi x a, and when we put n equal to minus 1, psi minus x, a sin minus pi x over a, which is minus a sin pi x, which is minus 1 multiply psi plus 1x. So that means the psi minus 1x equal to minus 1 psi plus 1x. So that means the quantum index n equal to minus 1 and n equal to plus 1, their corresponding eigenstates are linearly dependent. But as I said, one of the properties of the eigenfunction is they must be linearly independent. So one can choose either the positive side of the integer or the negative side of the integer. But at the same time, you cannot consider both positive and negative side. So using this idea, so in general, as I said, the psi plus nx equal to minus 1 psi minus x, where n equal to 1, 2, 3. So it means allowed wave function, which are known as eigenstates, are not linearly independent. Okay, it's not linearly independent. So, but as I said, one of the properties of the eigenfunction or eigenstates are linearly independent. So hence, we should either consider the positive side of the integer or negative side of the integer, not both. So therefore, um, for the eigenstates, okay, the final allowed eigenstates will have this provided n equal to 1, 2, 3 is quantum number. So these are the eigenstates. And in order to get the wave function, as I said, we'll construct from this eigenstate. So this will give the total wave function associated with quantum system, quantum particle or system. Okay, is it clear? Am I audible? Hello?
Sir, why it is that means it should be linearly independent, that wave function?
The wave function is not linearly independent. I am talking about the eigenfunction. This is
Sorry,
one
yes,
of the property. One
eigenstates.
eigenstates, their eigenfunction, they must be a linearly independent. One of the properties. I'm going to deeper in mathematical language. So let me give you the coordinate systems x, y, z. Okay. So coordinate systems. So if we have a let's say any vector r, we can write it in terms of I cap x plus j cap y plus k cap z. Yes or no? But x, y, z, they are independent because you cannot convert x in terms of y and y in terms of x. That means the projection of this vector r will have all components along x, y, z. But the projection of this x component will have nothing on y and z. So that case, they are sometimes called orthogonal and they are linearly independent. Okay, they do not depend with each other. But other variables, for example, the position vector will depend these things. So this is called the orthogonal. Sometimes people call orthogonality relation. That we already talked about electromagnetism. Okay, if you remember the electric field, magnetic field, propagation vector, they makes 90 degree with respect to each other. So in deeper sense, the eigenfunctions, they are like direction in a space called Hilbert space. That I am not discussing the Hilbert space. The wave function is actually in an Hilbert space, which is an n-dimensional space. Got it? Like here, the position vector is in three-dimensional space, x, y, z. Okay, and x, y, z are orthogonal. So Hilbert space, the wave function will be defined in Hilbert space, which are n-dimensional orthogonal space. And in each dimension, there will be eigendirection or eigenstate or eigendirection. So for example, we'll have these are all are orthogonal in Hilbert space. That means they makes 90 degrees in dimensional infinite space. This will be your psi 1x, this will be your psi 2x, this will be psi 3x, this will be psi 4x, and then they all are orthogonal to each other. That means the angle between any two eigenstates will be 90 degree. As I said, this is orthogonal. So it means the psi 1 eigenstate will have no component along any one of these eigenstates. Got it? But here, if psi 1 has component psi 2, that means we can you have convert psi 1x in terms of, let's say, a1 psi 2x. So that means the wave function, the eigenstate psi 1 has component psi 2x. It means they are not orthogonal. So it means they are linearly dependent. But the eigenstates which defines in Hilbert space that explain the total wave function is n-dimensional orthogonal space. So in that regard, the eigenstates are orthogonal. So therefore, they must be linearly independent. Got it?
Yes, sir.
So this Hilbert space, those who are interested, they can go through and look at Google on some of the standard quantum mechanics books. Okay. So, but in short, in summary, the eigenstates must be linearly independent. So now we got the eigenstates and therefore we'll get the total wave function. Okay. So now the final job is to find the energy values, and before that we need to normalize it. It means the square integral condition. the square integrable. So this is the total wave function, right? 1. We have 3 regions, minus infinity to 0, 0 to a inside the box, the left side of the box. This is the right side of the box. Third region is 1. As you know, the psi 1x, psi third x is 0. The wave function 0. So we have 0, 0 to a, psi nx, sin x dx. That means wave function inside the box 0 to a, which extends 0 to a square sin square n pi x over dx equal to 1. Okay, and all of you know how to do the integration. Finally, you'll get a equal to square root of 2 over a. So the normalized eigenfunctions or eigenstate is square root 2 over a sin n pi x over a, provided n equal to 1, 2, 3. You should write down the values of n. Otherwise, it will not be correct. And here, what is n? N represents the eigenstate index or quantum state index. And what is a? A is the length of the box. Okay, or we can say the width of the box or the width of the potential well. Okay, and what is x? X is the position of the particle inside the box. So now this is the eigenfunction. Again, I am rewriting it. You will get the total wave function by linear combining this eigenfunction, and that will give the total wave function and all the information you can extract from the wave function psi x. Okay, so now we values. So if you remember, we have this relation k square to m over h bar square. That here. So one thing I would like to again highlight here, we have not done any approximation. All those are coming from the derivations. So that's why it's exactly solvable. So k square is 2m over h square. So that we use here. Okay. And then we have already get k equal to n pi over a. Where? Here. K equal to n pi over a. So these two equations appear automatically when you solve Schrodinger equation. And combining this, we'll have this, and that will be equal to n square pi square h bar square 2m square. Okay, and since the quantum or state index is appearing here, so it is appropriate to use En. So En is the eigenstates, sorry, energy eigenvalue. So the energy eigenvalues or allowed energy levels En equal to n square pi square h bar square 2m square, provided n equal to 1, 2, 3. So so what does it mean? That means the eigenstate psi 1, which is 2 over a sine pi x over a, the corresponding energy eigenenergy is En equal to pi square h bar square 2m a square. And when psi 2 equal to square root of 2 over a sine 2 pi x over a, then the E2 will be 4 pi square h bar square 2m a square. And that means when an operator Q Q, so here this is the energy eigen operator I bar del h over, so del over del t. So this is energy operator. When this Q act on psi 1, it will give E1 psi 1. When it will act Q psi 2, it will give E2 psi 2. Okay, so we'll get the energy eigenvalues when the energy operator act on the wave function. And what we'll get that the En equal to n square over En. That means the energy eigen values or discrete energy level, they are not equispaced, right? So the if the first one, let's say I square a square over h bar square over 2m square, E2 will be 4E1 E3 will be 9E1 and so on. That means if you draw the energies, so let's say this is E1, this is 4E1, and then of course this will be 9E1 and so on. Okay, and the corresponding eigenstate will be psi1, psi2, psi3 and so on. And most importantly, the ground state energy is not zero, which is pi square h bar square 2m square. One of the characteristic feature of the quantum system, quantum particle. Non-zero minimum energy associated with the quantum particle. Okay, so in short, that we derived set of allowed energy levels, that means discrete energy levels, which is one of the properties of the quantum systems that we talked in the very beginning of the quantum chapter. Okay, you can use the same procedure to solve the rest of the problems. Okay, so I'll give this rest 4 problems as a self-study, right? And you'll find very beautiful lecture from YouTube. So those who are interested, they can look at these beautiful lectures. Okay, or you'll find some also some beautiful lecture. Probably I'll give the the links, right, and you'll go through it. Okay. So any question? Any question? So if there is no question, I think I should stop here. And by this, we are closing the chapter of the second unit, namely quantum physics. And as I said, the rest 4 problems I put as a self-study. And probably I'll upload the materials and you'll go through it. And you can also study yourself, looking beautiful lectures over YouTube. Okay. And in the next class, we'll be discussing the third unit, electromagnetic chapter. Okay. So that's all about today's lecture. We'll meet in the next lecture. So again, is there any question, in specific question? Okay, so if there is no question, I think I should stop here and we'll meet in the next class to discuss it. So bye everyone.
Thank you, sir.
Thank you,
Thank you,
sir.
sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.